Hello everyone, we are diving on into chapter 3 part 1. If you haven't already, I would watch the video on the properties of waves so that way you can have a good understanding of what the wave particle duality of light is when we get into that here in just a minute. And so here is the chapter outline. I crossed out the stuff that's the historical development. It's really interesting and it's, nice to know, but I would rather give you more time to work on how to do these math problems and wrapping your mind around the properties of waves. But it is an interesting read if you want to go take a look at it. We're not going to get to all these things in this particular video. Like most of what we're going to be talking about is electromagnetic energy and the properties of light. And so this is just a little review of what I talked about in the properties of light video. Remember, we had ideas like, we had terminology rather, like amplitude, right? Going from the non-zero, or going from the resting point of 0 up to the peak, right? It's not all the way from the top to the bottom. It's from this point right here, because this is what is considered 0. Then you have your peaks, your wavelength being the distance between those peaks, the period, the time it takes to get through one cycle, and the frequency being the inverse of the period, how many cycles per unit of time, usually it's per second. So if a period is 10 seconds, then how many cycles are there per second? Well, there's 1/10 of a cycle. Right? And so this video right here, this Khan Academy video, does a really good job of introducing the electromagnetic spectrum. And here you can see my chicken scratch of how a very simplistic, less artsy view of it than it is in the video. I suggest you click on the link and watch the video. But on one end over here, you have radio waves. Right? And then you have visible light in the middle. This is like the light we see as colors. And then you have X-rays and gamma rays on the farthest end of the scale. And the whole idea behind the electromagnetic spectrum is these waves, like radio waves, light waves, UV rays would be like the waves from the sun would be here. Oops. Let's put that in pen. UV rays would be right about in here. UV rays would be like right here. All these waves emit a certain amount of energy. And then you have microwaves. Microwaves emit enough energy to heat up your food. And then you have visible light, the light you can see. That is the frequency that is detectable to our eyes as color. UV rays we can't see because the frequency is too high for our eyes to detect as color, but we can definitely feel it if we have a sunburn and things like that. And so as you go from the left to the right here, your wavelengths go from being nice and long to getting shorter and shorter and shorter. And so the longer the wavelength over here, the lower, it should say lower rather than less, the lower frequency you have, the lower amount of energy you have. And so when people say things like microwaves can cause cancer, if microwaves were able to cause cancer, so would the ability to see light. Because the visible light spectrum has a higher frequency and be more capable of causing damage to your body than a microwave, because microwaves have less energy than visible light. And so when people say like your cell phone gives off like radio waves, you can get cancer from that. You can get cancer from standing too close to a microwave. If that was true, we would all have really terrible cancers because visible light would then be more dangerous than radio waves and microwaves. Okay, now UV rays, as we well know, the sun burning your skin too much in some cases can mess up someone's DNA enough to have skin cancer. X-rays can be dangerous, which is why X-ray techs wear those special vests. We've all heard, most of us have heard of Chernobyl, where there was the nuclear meltdown. The radiation that comes from there is so dangerous that people aren't even allowed there unless they're specially trained and they work there. And so electromagnetic radiation can be dangerous, but not at these levels over here to the left. Alright. So waves, you've already had a video talking about waves and what it is and examples of waves and the properties of waves video. And these we have also already defined in that video. And so if I had to take these waves and rank them from highest energy to lowest energy, well, the shorter the wavelength, right? Shorter wavelengths have higher frequency and higher energy. So this would be higher energy. This would be in the middle. And because it has a long wavelength, this would have the lowest or least amount of energy. Okay? So, frequency is usually expressed as cycles per second. The -1 simply means it's a fraction, so it would be like 1 over seconds. And so, another way to say that is seconds to the -1. That's all that means. So when you hear about frequency, it'll be in the unit of hertz because this is used to describe hertz. You will need this formula, so write it down. The product of a wave's wavelength and frequency is the speed of the wave. For electromagnetic radiation in a vacuum meaning there's nothing, no particles, there's no air because there's no nitrogen and oxygen and all that stuff. In a vacuum, any electromagnetic radiation, no matter what end of the spectrum it's on, travels at the speed of light. And that's a constant you're going to need to know. Like Avogadro's number, 6.022 times 10 to the 23rd is a constant we use a lot. This is another one of those constants. And so, you might need to do some practice problems with this. Such as this one here. An FM 95 radio station has a certain frequency. What is the wavelength? And so, when I look at any type of word problem in chemistry or even in math, I ask, what am I given? Okay, what is the information that the problem is giving me? What do I know? This is the section where I put my, my constants and my formulas. What are they asking me for? They're asking me for the wavelength. And it may seem silly to write this out for every problem, but some problems you're going to get extra information that you don't need. And so if I look at this formula where I am talking about what I know, I already know the speed of light. I already know the frequency, so all I need is the wavelength. So I can tell here that I have everything that I need to solve the problem, and I can also tell I don't have any extra information that I need to disregard. And so here I set up the formula, speed of light equals your wavelength times your frequency. You divide by the frequency in order to isolate the wavelength, and your answer to this should be about 3.51 meters. Where did I get meters from? Well, meters comes from the speed of light because you have meters per second here. All right, so here's another practice question. An FM radio station found on 103.1 has this frequency. What is the wavelength of this radio wave? And so using that same method again, what am I given? What's my given? Well, my given is 1.03 times 10 to the 8th. This would be hertz, but seconds to the -1. Well, what is this? This is frequency. Alright, so, or frequency. Alright, and what do I know? Well, I know that the speed of light equals what? 2.998. It's 10 to the 8th, right? Yep. Times 10 to the 8th. Oops. Times 10 to the 8th meters per second. And this is my formula. Alright, and what are they asking for? They're asking for wavelength. That's what they're asking for. And so I'm going to set up the formula like I did in the last problem. And then I know that this is my speed of light. And I'm looking for my wavelength, and my frequency is 1.03 times 10 to the 8th seconds to the. And this is how you know that when you divide by this is what cancels out those seconds and gives you meters, or leaves you with meters. Right. So I'm going to type that in my calculator here. So 2.998 times 10 to the 8th divided by 1.03 times 10 to the 8th. And that's going to get you about 2.91 meters. Alright, so that's just a few practice problems for you. And this is just showing, it, so up here I showed it from longer wavelength to shorter wavelength. Alright, radio waves was to the left. And this one they just flipped it. It's the same information. And so these are some of the properties of the electromagnetic spectrum, and this they show like the visible light where you can see light, X-rays. Over here on this end is where you would find electromagnetic radiation from like nuclear power plant meltdowns and things like that. This is where you're going to find the frequencies that can cause bodily harm. Visible light doesn't, if something's too bright it hurts our eyes, but just seeing colors is not going to give you cancer, and anything down here on this end is also not going to give you cancer. And so this is just these waves and how they transmit energy, and these are just examples of how that applies to our lives.